The end of 4.2. And the slide may say mean value theorem, but that's not what we're going to do right now. We're going to mess around with a corollary and a theorem. Corollary? How do they say it in England? It's really strange. I can't ever get it out of my mouth. But who am I to talk shit? I think they're the one that came up with the English language anyway, so maybe I'll just shut up and move on. Alright, moving on. We get down to our theorem and a corollary. Let's start with our theorem. Our theorem's pretty freaking straightforward. It's one of those kind of like, oh, no shit. I mean, once you can get through all the words and the notation and shit, it's pretty freaking straightforward. So we're saying if the derivative is equal to 0 of some function f for all the x in the interval, then f is constant on that open interval. Come on, dude. Come on. A, B. Now, what does it mean for the derivative to equal 0? For everything in between A and B. It means that shit's flat. Look at the pen sitting on top of your table. It's not rolling off. It's flat. The derivative is that, so it's... Oh, so it has a constant value. Y is equal to some constant. It has the same height, right? We're talking about this is the y-axis, and this is our x-axis. I think that's pretty friggin' straightforward. The derivative equals 0. That shit's flat, and you just have a constant as your functional value. Moving to our corollary. Now this is a little more in depth. I think requires a picture, maybe a little explanation. And this is more of what we're going to use. Now this is saying if the derivative of f is equal to the derivative of g, two different functions. But this is true for all of their values. They have the same freaking derivative for all x in some sort of interval. Open, of course. Then when you actually take their functions, not their derivatives, and you find the difference between their values, it's going to be constant for that same interval. Or we could say that f of x is equal to g of x just plus some constant, or c is, constant. Just keep saying constant. Let's check out a picture, yeah. So I've drawn up something here. Well, we have two functions. We got our function f, and we got our function g. Now I've tried to set them up. They're not exactly perfect, but try to set them up where they have the same exact slope. Derivative for every value of x in between those points A and B. They're supposed to be mirroring each other. So when one changes has a slope of 2 between -2 and 1, I don't know what the freaking numbers are. They all match, right? If this is the case, now that would mean that there's a difference between these two that's just constant, right? It's always changing. If they're always changing by the same amount, like didn't we have that when they had the same slope? Shit was parallel. When you have the same freaking derivative, it's going to change the same way, even if it is a curve, at least for all the values of x. So we actually have this constant difference, this c. Well, what this big that big thing back here, what was it talking about? That if our derivatives are equal to each other for all x in that open interval, looks like that's the way it is, then f minus g is constant. There's those little c's that keep popping in. And then let's look. That is, the function f of x is equal to g of x plus some c, plus some constant. So this is saying f of x minus our g of x. Oh, no. Let's say that our f of x is actually equal to our g of x plus that silly little constant. And that's going to be true, right? Because we're saying from g of x, we go some distance up to g of x. Now we still got to go c more to get up to f of x, right? We're adding it up. Now this is going to be true for all x in that interval between a and b. True? So we've just shown why that corollary works. That if they're changing at the same rate, then they're going to have a constant difference between the two. All right. Now let's get into maybe more of a problem you might see in the text. This is very similar to example 6 on page 291 of your book. I like this one. You probably can tell right away why I like it. Hey, we're going to prove the identity. The inverse sine of x plus inverse cosine of x is just equal to that constant, pi over 2. We're going to say, ha, that's true, huh? And we're not going to use trigonometry for this one. By using trigonometry, we should be able to already solve this. With trigonometry, we know that inverses are angles, right? Don't we know that inverses are angles? Sorry if I sound so disjointed. I get my dog up chewing on a bone next to me. I didn't think he wanted to listen to that. I lost my place. So sine inverse of x, that's an angle. Inverses are angles, and cosine inverse of x, that's an angle as well. And actually, they're complementary angles. If you make a triangle and take a look, you'll be able to tell that these are complementary angles we're talking about here. And complementary angles add up to be 90 degrees, pi over 2. So through trigonometry, we can solve that. But we're going to use a little calculus to show this. We're going to show the complementary angle theorem is true here. So why don't we just call our function, let's just call it sine inverse of x plus cosine inverse of x. Cool. Take a derivative. We're in calculus, can't hurt my help. So we get 1 over the square root of 1 minus x squared, and we're going to add that to our derivative for cosine inverse, which are absolutely freaking opposites, are they not? So we get that its derivative for all values of x. For all values of x, well, actually, I can't say that. Oh, wow, am I being sloppy right now? I think our values of x for these ones are only going to be in between -1 and 1. So f prime of x, because that's the domain of the function, and that's where this function is also differentiable. That's where I can talk about any of the endpoints. Okay, that's neither here nor there. So we have found our derivative to equal 0. Now, what the hell does that mean? If the derivative is equal to 0 for all x in an interval that's open, we have one from -1 to 1, then we say that f is constant. That means it has the same freaking value the whole way through. So all we have to do is pick any value we freaking feel like. I don't know. Maybe we'll pick 0. You know what I mean? Plug it in, see what the hell happens. We'll see what pops out. And that will prove, because we've already shown by our little theorem, that if this is true, we found that the derivative is equal to 0 for some open interval, then that means that this f of x must equal a constant, some sort of constant. Well, let's go show that that c is absolutely equal to pi over 2. So all we need to do is plug in any value that's in our domain. So let's say sine inverse of, and I've already told you the value I'm going to plug in, cosine inverse of. Now, if we plug in 0, I like that number. 0's a good one. All we got to know is a little bit of our trig, and now sine inverse of 0 is equal to 0, and cosine inverse of 0 is equal to pi over 2. Therefore, this shit's equal to pi over 2. And by using this theorem, we have now shown that our c must equal pi over 2. And I'm going to show you with one more, just so you're not thinking I'm using some voodoo here. Let's go with cosine inverse, and let's do it again. Let's choose pi over 4 this time. Oh, not pi over 4. Shit, what the hell am I thinking? Let's say, damn, I'm giving away my trig. Root 2 over 2. Root 2 over 2. Root 2 over 2. I think that both cosine inverse and sine inverse are equal to pi over 4 in both of those places. So that was not some sort of voodoo or weird shit I'm trying to pull off on you. No, we used a theorem saying that if the change is 0 for all values, if the change is 0 for all values, that means we must have a constant. It's not changing, right? There's our last little game. There's our last piece of the mean value. I really like these games. Please take a look at these. There's a cool one with tangent inverse and cotangent inverse. You can also do this with secant inverse and cosecant inverse. All right, I'll see you in the next section.